Okay, hey guys, this is Mr. Sheeling. This is going to be that in-class walkthrough that we did in class together, working on number 1 here for worksheet number 4. So I'm going to quick read out what number 1 says to you guys. A blast furnace burns with enough heat to react iron 3 oxide with carbon, producing solid iron metal and carbon dioxide gas as shown in the reaction below. So we've got the reaction down here, and again, I lay out all 3 things I want you to look for. So the first thing that we've got to look for here, we've got to look for the limiting reactant. Okay, what is the thing that's going to run out first? We also need to find out what the mass of iron, the iron that can be produced. So how much of this stuff do we predict will be made? And then what is the mass of the excess reactant left over? So after we've figured out who is going to be running out first, who is going to be the excess reactant, we're then going to take the number of moles that will be left over, and we're going to then find the mass. So here's what you should do. So we've got all this gunk that's in the way of our balanced reaction. So we're just going to rewrite it down here real quick. But we're going to write it decently big and a bit spread out so we just have enough room on our BCA chart to have all of our info. So I'm going to start like right here, 2Fe2O3 plus 3C yields 4Fe plus 3CO2. Okay. I'm just going to quick make my BCA chart. All right, so it looks like here that this is what we're starting off with. We're given 65.7 grams of carbon. We're given 175 grams of iron 3 oxide. So the first thing we have to do, because we're not given moles of this stuff, we've got to convert our reactant, the grams of our reactant, to moles of our reactant. So we're just going to start with carbon first. So carbon, we've got 65.7 grams of carbon. We have to convert that bad boy into moles of carbon. So we want to go from grams to moles. And just to give it to you, if you were to look on your periodic table, you'd see that the molar mass of carbon is 12 grams for every 1 mole. Okay, we'll leave that just for a second, and then let's just set up for iron oxide. Specifically iron 3 oxide, so it's going to be the Fe2O3. Starting with 175 grams of this stuff. We got to convert that into moles as well. Okay. And that bad boy has 159.6 grams for every 1 mole. Okay. Here, and I'll hide this little thing real quick. All right. So when we divide 65.7 by 12, we should get somewhere roughly about 5.475 moles carbon. And then when we divide 175 grams by 159.6 grams, we get something like 1.096, we'll say 649 moles of our iron oxide, our iron 3 oxide. Okay, so that's what we're working with. So we might as well, because we know this is what we're working with, let's just slap these up top to where they belong. So this is the number of moles of the iron oxide, so I'm going to put that up there. 1.0 in the before line. 1.09649, and the number of moles of carbon, 5.475. Since it's the before line, we put zeros underneath our products. Okay. And then now let's figure out who our limiting reactant is. So we're going to divide the number of moles by the respective compound / respective elements coefficient, the number of moles in our balanced equation. So for carbon, looks like it's 3. And then for the iron oxide, it's 2. And what we should get is, for carbon, we should get about 1.825. And then for our iron here, just to double check on it, 1.09649 divided by 2. Should get about 0.548245. That's what we should get. So clearly our limiting reactant here is going to be the iron oxide. So our iron oxide is going to be the first one to run out. Okay. All right. So because we know iron oxide is going to be the guy that runs out first, we're going to use that multiplier that we've got right here. We're going to use this dude to multiply against all of the coefficients here, because this is going to determine how much of this stuff will get used up, which is everything, how much of this stuff will be used up, how much of this we expect to be produced, how much of this stuff we expect to be produced. So it'll be 2 times the 0.548245. Here will be 3 times the 0.548245. Right here, 4 times 0.54845, and then another 3 times 0.548245. Okay. So then on the change line, for this guy, we can just input this back in because we know this is going to run out. This is going to be 0 moles because it's our limiting reactant. So, and in order to get that 0 moles, we know that it has to be just 1.09649, right? Now for 0.5, for our carbon, 48245, 1.644735. That's what's awesome about this is that, well, it's 3 times this number here, so, and over here it's also the same thing, so we can just slap that in over here. Don't have to do the same work twice. Okay. And then we'll just quickly get this guy. And it's going to be 2.19298. So easy peasy on these two, because it's just 0 plus this, 0 plus this. So here for iron, we should expect that we should get 2.19 moles of iron, and we should expect to get roughly about 1.64 moles for our carbon dioxide. Okay, and then for our excess reactant, it's going to be 5.475 minus this number, 1.644735. It looks like we should expect to be left over with 3.83 moles of carbon. Okay. So now we only answered the first question, which was this, and I didn't highlight it, but we did answer the first question here. Okay, that's our limiting reactant. Remember, that's the one that is going to be used up first. So now we have enough information to answer B here and also to answer C. What's the mass of the iron that we expect to be produced? So we're going to take this bad boy and we are now going to convert the mass of iron into moles of iron. So mass of iron produced. Okay. So it'll be 2.19 moles iron. And we want to convert moles to grams. In every 1 mole of iron, there's 55.8 grams. Pop this in the calculator, and what we should get as our answer, keeping sig figs, it would be 122 grams of iron. So we expect that throughout this whole process, that we should expect to have 122 grams of iron left over. And then to answer the final question here for C, what is the mass of our excess reactant? Well, our excess reactant is going to be the carbon. And we know that looking here on our BCA chart, we expect that we'll have 3.83 moles of carbon left over. And then we just have to convert moles of carbon to grams of carbon. There are 12.0 grams of carbon in every 1 mole. Figure this out, pop it in our calculator, and we should get this. We should expect to have 46 grams of carbon left over. And then we have answered that final third question of how much mass we should expect to have from our leftover reactant. Okay. And then that is that. So for an outro, thank you guys for watching. If you guys still have any questions for me, make sure you ask me. If not, I'll see you in the next one.